The James Webb Space Telescope is set to revolutionize our understanding of the universe, and this $10.1 billion device is already surpassing expectations. Over the past 2.5 years, its discoveries have repeatedly challenged our fundamental understanding of the cosmos, proving that much of what we thought we knew is either incomplete or incorrect. The telescope has detected galaxies that, according to our existing models, should not exist. It has also revealed gigantic early black holes with inexplicably high masses and even an exoplanet where life may already be flourishing. Webb has become an instrument of cosmic surprises, proving time and again that we must expect the unexpected, or rather, the impossible. One of Webb's most shocking findings has been the discovery of several early galaxies that have completely overturned our standard model of cosmology. The first, galactic earthquake, to shake the astronomical community came in early 2023 when Webb identified 6 massive galaxies existing just 500 to 700 million years after the Big Bang. Yet, despite their early formation, these galaxies were already as massive as the Milky Way is today. Experts had long believed that only tiny, baby galaxies should have existed during this period, but instead, they encountered immense structures, some containing more than 10 billion solar masses of stars and one even exceeding 100 billion solar masses. These prematurely massive galaxies earned the nickname universe crushers because, according to our understanding, they shouldn't exist. Our models indicate that there wasn't enough normal matter in the early universe to form so many stars in such a short time. This means that either the matter density of the young universe was 2 to 5 times greater than our current assumptions suggest, or that stellar clusters formed through an unknown process. Either way, the standard cosmological model is being stretched to its limits. Webb's findings did not stop there. In February 2021, the telescope uncovered another early galaxy that defied expectations. This one contained 4 times as many stars as the Milky Way, despite being observed at a time when the universe was just 11.5 billion years old. Many of its stars had likely formed 1.5 billion years before they were detected, adding yet another layer of complexity to our understanding of galactic evolution. These anomalies have left astronomers grappling with the realization that the early universe may have been far more dynamic and complex than previously thought. The puzzle of the early universe extends beyond galaxies to the enigma of supermassive black holes. Webb has revealed an abundance of these objects, which are also deemed astronomically impossible, given their extreme masses at such an early stage of cosmic history. For a long time, researchers believed that supermassive black holes grew gradually by accreting mass from their surroundings. As matter falls onto a black hole, it forms a rotating, hot accretion disk that feeds the object at its center. In cases where the black hole reaches millions or billions of solar masses, an active galactic nucleus, or quasar, is formed. The energy released by this accreted matter generates radiation, which exerts a counterpressure on the inflowing material, effectively regulating the black hole's growth rate. This process suggests that black holes cannot grow arbitrarily fast. However, Webb's observations have shown that many early black holes reach staggering masses far too quickly. One such black hole, observed by experts at the Max Planck Institute for Astronomy, resides within the most distant known quasar at the time, designated J120+0641. This quasar existed just 770 million years after the Big Bang and contained a black hole with a mass exceeding 1 billion solar masses. Scientists initially hypothesized that early black holes must have grown through an unknown hyper-efficient feeding mechanism, but when they analyzed this particular quasar using Webb's mid-infrared instrument, MIRI, they were stunned to find that it was shockingly normal. In other words, this young supermassive black hole grew in the same way as modern quasars, contradicting the idea that early black holes had an extraordinary growth advantage. This leaves scientists with the troubling realization that they still have no clear explanation for how these objects reached such enormous masses so quickly. Webb's revolutionary discoveries extend beyond galaxies and black holes to rogue planets, worlds that drift through space without a host star. These planets may have been ejected from their home systems after formation or may have never been gravitationally bound to a star in the first place. In the fall of 2023, Webb identified a bizarre class of rogue planets in the Orion Nebula that completely defies expectations. Located 1,350 light-years away, the Orion Nebula is one of the most active star-forming regions in our galactic neighborhood. While previous observations had revealed solitary rogue planets, Webb discovered an entirely new phenomenon: planetary pairs. Specifically, the telescope detected 40 pairs of Jupiter-mass objects, referred to as Jupiter-mass binary objects, jumbos. The existence of these paired rogue planets is perplexing. Some researchers theorize that the jumbos formed in a region of the Orion Nebula with insufficient hydrogen to produce full-fledged stars, meaning they might represent a population of failed stars. Another possibility is that these gas giant planets originally formed in conventional planetary systems, but were later ejected by an unknown gravitational event. While the latter scenario is considered more likely, it remains unclear why the ejected planets ended up in pairs. Some scientists even speculate that this is not a mere coincidence but rather evidence of a yet undiscovered cosmic mechanism that produces binary rogue planets. If this is true, the Orion Nebula may not just be a stellar nursery but also a dedicated jumbo factory, forming these objects through a process that we have yet to understand. Webb's discoveries extend to even the smallest celestial objects. In February 2021, the telescope detected an asteroid only 100 to 200 meters in diameter within the asteroid belt between Mars and Jupiter. This finding was a stroke of luck, as the research team had originally set out to calibrate Webb's instruments by observing a different asteroid. Due to its exceptional sensitivity, Webb was able to detect this tiny object from a distance of over 100 million kilometers, demonstrating its ability to study small asteroids that were previously beyond our reach. Given that the asteroid belt contains primordial material from the early solar system, such observations could provide invaluable insights into the formation and evolution of our planetary neighborhood. Finally, one of Webb's most tantalizing discoveries comes from the exoplanet K2-18b, located 125 light-years away. This distant world is thought to be a Hycean planet, a theoretical class of ocean-covered exoplanets that could support life. Using Webb's near-infrared spectrograph, an IR-SPEC, scientists detected dimethyl sulfide, DMS, in K2-18b's atmosphere. On Earth, DMS is predominantly produced by biological processes, making this an intriguing potential biosignature. However, the DMS signal captured by Webb was relatively weak and only became apparent when the data was processed in a specific way. To verify this result, researchers constructed models simulating K2-18b's oceanic atmosphere and analyzed how much DMS could accumulate in its environment. Their calculations indicated that for DMS to be present at detectable levels, the planet's hypothetical organisms would need to produce it at rates 20 times higher than their earthly counterparts. The challenge with confirming extraterrestrial life based on DMS detection is that the compound's spectral signature overlaps with methane. To obtain a clearer reading, scientists plan to use Webb's mid-infrared instrument, MIRI, which operates in a wavelength range more suited to isolating DMS and its degradation products. If future observations confirm the presence of DMS, it would be one of the strongest pieces of evidence yet that life exists beyond Earth. In just a few short years, the James Webb Space Telescope has fundamentally reshaped our understanding of the universe. From uncovering impossibly large early galaxies and black holes to identifying rogue planets and potential biosignatures, Webb has continuously challenged the limits of modern astrophysics. As scientists continue to analyze its groundbreaking data, one thing is certain: the universe is far more complex, mysterious, and awe-inspiring than we ever imagined. Perhaps one of the most tantalizing discoveries made by Webb so far is the potential biosignature detected on the exoplanet K2-18b, located 125 light-years away. This world is suspected to be a fully developed ocean planet. Thanks to Webb's near-infrared spectrograph, an IR-SPEC, scientists found traces of dimethyl sulfide, DMS, in its atmosphere, a sulfur compound typically produced by living organisms on Earth. While the DMS signal wasn't particularly strong, researchers are now using Webb's mid-infrared spectrometer, MIRI, to further investigate. If confirmed, This would be one of the most significant breakthroughs in the search for extraterrestrial life. As Webb continues to scan the cosmos, we are reminded that the universe is far more complex and mysterious than we ever imagined. With each discovery, our understanding is pushed to its limits, forcing us to rethink our fundamental assumptions about the cosmos. Stay curious, stay amazed. Subscribe to Space Lab for more mind-blowing discoveries.